Hi, today we are going to check for divisibility and we are going to understand how simple it is to be able to ascertain whether a number is divisible by some other numbers. So straight away we'll go into these notes and we are having this title checking for divisibility. So the definition is this: let a not equal to 0 and b be integers. We say a divides b by denoting it this way if and only if there is an integer k such that b is equals to k times a. So that is very straightforward. We already saw that one in class. So we want to check for divisibility. We have an experiment here. It is stating that determine whether 3 divides b, where b is this very large number. Now you need to note that sometimes computers or this electronic gadgets might not be the best option because they might not be having the capacity to store or handle some of these numbers. If you try your calculators, you'll see they have some limits in which they can store this information. And in this case, number theory would help us solve some of these puzzles. Now, using computer may not be a very, very good option in this case. And then it is faster by using divisibility properties. So you can say this is some billions and billions or quintillions, I don't know. But then how would you know that it's divisible by 3? Simple. Now there's a theorem here and it's a criteria of divisibility by 3. It states this way: let b be an integer. 3 divides b if and only if the sum of the digits of b is divisible by 3. So we are trying to say that we'll know if this is divisible by 3 if we add all these digits here. If they're divisible by 3, then it's divisible by 3. Now the good thing is that in this case we know that all this is not important. 1 is important and all this is not important also. So it means that when we add 2 plus 3 is equals to 3. So is 3 divisible by 3? Yes. So we can say that this whole number b is divisible by 3. That's how quick we can move with this criterion. So add the digits, zeros can be or ignored. So that is what is happening. Now we have a second example here. We want to consider whether this number is divisible by 3. So what happens is this is the same principle. You add all the numbers. Are they going to be divisible by 3? If the resultant answer is divisible by 3, then it is divisible by 3. See, this is what happens here. We add all the digits of b. So 9 plus 5, blah, blah, to the last n. We get 83. We might not know whether this is still divisible by 3. So we can again add this 8 plus 3. And then we see whether 8 plus 3 here, which is 11, is 11 divisible by 3? It's not. So in that case, we can say that 3 doesn't or is not divisible by this number. Oh, 3 does not divide 11. So that is what happens. 11 is not divisible by 3. Yes, so that is very clear. So it's very simple for us to see what usually happens. So we further improve this criteria. Now this is the conclusion. That's how we come to it. We further improve this theorem by saying that instead again of doing what of adding all these numbers. If there are any multiples of 3 in this number, they can be cancelled out and the remaining numbers be added. How? That can be done by doing this. For example, if this is the number, we will cancel this is 9, 6, 9, 3, 9, and 9, and then add the number. If you get it's divisible by 3, then you know that. Now, this is what it says, that the sum of the digits of B different from 0, 3, 6, and 9 is divisible by 3. So you can ignore these numbers. These are what can be ignored in the long list. So if you get a very large number like this, don't worry a lot. If you are to determine whether it's divisible by 3, the only thing you do, you can cancel, for example, all the 9s, because 9s are divisible by 3, all the 6, and then there's another 6 here, there's 0 here, 6, all these are cancelled, there is a 3 here. You go all the way to the end. So once you get to the end, you will add these numbers. So once you added the numbers that have remained, you will get something like this. Now this might not be still clear, but the good thing is that there is a 6 here. You can still cancel it and see is 3 divisible? Is 14 divisible by 3? Or does 3 divide 14? Or if still you cannot understand, you can add this number 1 plus 4 so that you can see the resultant answer is 5. So you'd ask yourself, does 3 divide 5? No. So we can state here as a conclusion that 3 doesn't divide B. That's what happens. So the criterion by 3 is that all the multiples of 3 are cancelled out, and then the remaining integers or numbers are added up, and then we see whether they're divisible by 3. Even when you get the answer, that answer, the numbers can again be added to help us see what is happening. If you get a multiple of 3 there, you can cancel it. That is a criterion of divisibility by 3. Now, the criterion of divisibility by 2 is very simple. We've used it all along. We know it if the last digit is an even number. So if it's even, then you know that it's divisible. So that's very simple. Just look at the number and then you know that, well, it's divisible by that. So this is what is happening. Theorem of divisibility by 2. Let B be an integer. B divides B if and only if the last digit of B is an even number, is 0, 4, 2, 6, or 8. So you can look at this number. If 2 divides B, let B be this number. When you look here, yes, this is an even number. Yes, 2 will divide this number. So no need of checking that. So that is very simple. So divisibility for 4, 5, 6, 7, 8 is also applying more or less the same principle that we've learned for 2 and for 3. And we'll add some other few things here. Now, for example, the criteria of this divisibility by 4, we state that the theorem states that let B be an integer. Okay, 4 divides B if and only if the number formed by the last 2 digits of B is divisible by 4. So what we're looking at is the last 2 digits of B. Is it divisible by 4? That's what we are looking at. Now there's a hint here that from 1 to 100, all the numbers divisible by 4 here. 12, I can call them multiples of 4 or something like that. So we have 12, 16, 24, 48, blah blah, 88, yes, to 96. So what happens when you look at a number like this? You see this is 56, for example. If you know that 6 is here, then you know that it's divisible by that. So it's very, very simple. Or else, if you're not very sure, you can still divide it by hand and see if it is divisible. So that's it. So criterion of divisibility by 5, it's simple. It states that let B be an integer. So 5 divides B if and only if the last digit of B is either a 0 or a 5. That's very simple. You look at this number, can this one be divided by 5? You look at this last number, yeah, you know that, yes, this is divisible by 5. That's what you only look at. If it's a 0 or 5, then you know that everything is fine. So 5 divides this number. So it doesn't matter how long the number is. Now 6 is here. It says that the criterion of divisibility by 6, so let B be an integer. 6 divides B, and 6 divides B if and only if 2 divides B and 3 divides B. Now you note that 6 here is a multiple of 2 and 3. So we're going to put these two criterions and use it here. So we are going to look at an example here. For example, you look at this number. Check whether 6 divides B. So the first thing is that does 2 divide this number? We look at the last number. It's what? It's an integer. It's an even number. So definitely 2 divides this number. And then we go to this one. Does 3 divide this number? What happens? We come here. We can cancel all the 3, all the 6, all the multiples of 3, and then we can add this number. Once we add that number, we will get the number is 57. If you're still not sure if 3 goes here, you can add this two number. 5 plus 7, it's 12. So 3, yes, divides 12. So that's how we can check for divisibility by 6. 6 is a multiple of 2 and 3, and we've seen these two criterions beforehand. It's easy for us to really note how that happens. Now the close to final is a very interesting one, is the criterion of divisibility by 7. We state here, it says that let B be an integer. 7 divides B if and only if the number x minus 2y is divisible by 7, where y is the last digit of B and x is obtained from B by deleting its last digits, or less the same thing. Now let's look here. What happens? We have now some variables here that we want to take note of. We have one is x, another one is y, and there is this expression here, x minus 2y. So what happens? We have the number that we are trying to evaluate right here. So we come with this table that has got a number y, x, and x minus 2y. So what happens? We put the number here. So we state that y is the last digit of b. So b is this number. Y is the last digit. X is the last digit minus the last is the whole number minus the last digit, which is this one. And this function here or expression is x minus 2y. So we know x is this, and 2y is this. So it is 2 times 0, it is 0. So the number remains the same. So it is this number minus 0. Okay. So what happens? Now our current value number is this. So this is our new number. We bring it right here. The next stage. So this number y, we say the last digit, we keep it here, and x is this number minus the last digit, it's here, and this is x minus 2y. We have our x here. 2y is 18. 2 times 9, so minus 18. So if you put 18 right here, if you subtract 18 there, for example, since you get 11 minus is 3, and then those 9 minus 1 is 8, and then you have this is now 7, a 7 and a 7, under 2. Okay, so that's how we get this number. So this number, take it here again and do the same. We keep on we keep on subtracting the numbers that come. We will get to 21, and we know that 21 is divisible by 7, and that's how we get to know that this number is divisible by 7. So that is it. And finally, for divisibility, we have a criteria for divisibility by 8, which states that let b be an integer. 8 divides b if and only if the number formed by the last 3 digits is divisible by 8. So you only look at the last 3 digits. So these digits divisible by 3. So we know very well that 2 goes into it 3 times. So we can buy this number 3 times by 2. 3 times by 2. So this is what happens right here. We have this number. It's 376 divided by 2, it's 182, and then 188, sorry, 188 divided by 2 is 94, and 94 divided by 2 is 47. So we get to know that for sure, yes, it is a divisor here. So that's what happens. So that's how it can be done. So at times when you want to sort out these numbers, you can see with your hand, you can use your hand and see with your eyes, and then you can know whether a number divides or not. That's very important, and it's going to be tested. Now we have something important here. Finding all divisors by hand. It's like stating that we can just find all divisors of a number by using hand. But now we have a theory here, which it states that let n be a natural number, yes. And then the goal is to find all divisors of n for n small, so meaning that just a number which is not very large. So what happens here, we have this theorem here that let n be a natural number, and then if d1 divides this number, then there's a unique divisor d2 of n such that n is equals to d1 times d2. Yes, that one we already see. So we have two divisors. So what we're implying here is that divisors of n come in pairs. So in a number that is going to be divided, and if it's got divisors, then they come in pairs. So that is what happened. And one of the divisors is less than the square root of the number. Yeah, the square root of the number. So in most cases, you get that that number is as let's say it's 100. It's either 10, 10, or it can be 20 and 5. So you see, 20 times 5 is 100 times 5. So one of the numbers, one of the divisors is less than the square root of the number. So 100 square root is 10. So this is of course less than the square root of the number. So that is actually what happens. So this is what we're trying to say here. If d1 and t2 are in 1, then d1 is less or equal to the square root of the number n, and d2 is less or equal to, or actually here it's or d2 is less or equal to the square root of the number. So any can be less or equal to, actually any one of them is supposed to be less or equal to, if not them being equal, like 10, 10. So that's what is supposed to happen. So this is a proof to actually validate this statement that we're saying here. So maybe I can just bash or go through it quickly. If d1 divides n, then there is a unique divisor d2 of n such that n is equal to d1 times d2. Yes, that's true. We assume that d1 divides n. Okay, that's fine. So by definition of d1 divides n, then there's of course another integer d2, so that n is equal to d1 times d2. Yes, that's true. So d2 is completely determined by n and d1. Yeah, that's very true. You can play around with this. You can now say that, for example, if you are looking for d2, you can divide d1 on both sides, and then you have the d1 coming here, something close to that. So that's why we have d2 is n over d1. Now, we just want to test something here. If d1 and d2 are in 1, then we've just seen this one, that d1 is less or equal to the square root of the number, or d2 is less or equal to the square root of the number, which is very true based on this example here. Now, the final thing is that we have something, the proof of contradiction. You change some of the signs, you contradict yourself to prove something. Now, for example, now in this case, we are stating here that that now in this case d1 is greater than the square root of this, and d2 is greater than what? The square root of this n again. So in this case, we will definitely know that d1 times d2 is greater than the square root of this number also multiplied. So in this case, we are trying to find n. Once we multiply the two square roots, we get n. So n is less than d1 times d2. Of course, there's a contradiction, and it's not right, but it proves that a statement is right. So this is what we call as a proof by contradiction. Now, that is what happens, but it's not very important now, but just to note that one of the advisors is supposed to be actually less or equal to the square root of that number. Now, that is very, very, very important. Now, an example here, we need to find all positive divisors of 60. Now, we know that very well that the square root of 60 is somewhere close to this 7.7. I think I have a calculator here. I have a 60. Let me see. Where is the square root? Okay, it's just right there. It's 7.74, blah blah, all these long numbers. So we know very well that one of the numbers is supposed to be actually less than 7. So we will need to check for 1 to 6 only. We need to check the 7 because it's actually above what we are trying to look for. Now, the best way to go about it is just simple. It's just simple, finding all the positive divisors of 60. What happens is this: we draw a table whereby we have 3 columns. One is divisors less than or equal to the square root of 60, and divisors bigger than or equal to the square root of 60. And then we have the pairs right here. So that is going to help us to find all the divisors of a number. So for example, 1 goes to 60 once, that's 2. 2, it goes 30 times. So we put the pairs here, 2 times 30, all the way down to actually 6, which goes there 10 times. So it's 6 times 10. These are the pairs. These pairs are the ones that actually reduced to arrive at 60. So 1 times 60, 6 times 30 is all the way down here. But then all the divisors, how we get them, you just, of course, see all these numbers all the way up like this. So it's actually 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. So that's how we can get all divisors of a number. So we have actually 12 positive divisors. So this one calculator to rule them all, actually we're just trying to talk about Pari. Pari actually is a text-based calculator. Console meaning it actually works with commands. Now, because of time, we'll not be able to go into its detail, and we'll use the actually freeware or the one that works with on the browser. If you're connected to the internet, you can always use it at any time. You just open your browser, and then actually you just type ParityP like that, and then you open this, actually more or less the first result that comes. Once you get to ParityP home, you go to this side, this left side column of your browser. You see Pari in your browser. So Pari in your browser, you're right here. So right here, this is where we put our texts. And if you put our texts here, it means that we're going to evaluate it and we're going to get results here. So we've been trying to look at devices, primes, and many other things, and then we can use this one for that work. So the reason why Pari is very important, it's one of the fastest, and then it has lots of functionalities with actually number theory problems, and then it's free. It's one of the best things for us to do. So for example, now we want to know prime numbers. We are going to use Pari in this case. Now, introduction to prime, we know what a prime number is. I don't know if you still remember what you did in your elementary mathematics. Now, we know very well that prime numbers are one of the most important concepts in number theory, and they have applications not only in number theory, but also in communication. That's why they use for security now, or cryptography. Now, it's very important for us to know that the definition is that an integer p is called a prime number if it has exactly two positive divisors. And we say that it's one and itself. That's a number that divides, is divided by one and itself. That's what we used to state. So an integer, and which is not zero, that has more than two positive divisors is called a composite. So that is something we want to look at. Now we will use the term prime to refer to the positive prime numbers. In our case, we are only going to use prime positive numbers, so positive prime numbers. So starting from 2 all the way we go to, I don't know what you might want, but then these are all prime numbers. So for example, you go to Pari and then you just type here prime, and then you say 100. You can evaluate using this. Okay, it says that there are around 541. No, something is up here. I just need to confirm yes, and then we'll look at it some other time. Okay, let me just have a separate tutorial for this. Guys, thank you.